have the plane that's traveled 255 meters, takes off, travels up into the air at 25 above the horizon. At the point when it's traveled 157 meters, we want to know its resultant velocity. So, that resultant velocity forms a right triangle, does it not? Okay. So what we're going to do is we're going to break these two components. Okay, some of you see it. Good.
No, I said I don't.
Oh, you don't. Okay, well that's fine. So what we're going to do is we're going to break this piece of its travel into its x and y components. And now we have an overall larger right triangle that we can work with. So here's where your bookkeeping gets real important. So we're going to talk about segment 1 here. So for segment 1, we have a delta x of 255 meters. We have a delta y of 0 meters. There is no y component to that first segment of travel. Would you agree? Wunderbar. Good. I'm glad to hear that you agree.
What does that mean?
Oh, wonderful.
What language is it? German?
Yeah.
We've been wondering that since like the whole year.
Sorry.
It's like Spanish.
Habitual. Okay. For segment 2, we have a delta x and a delta y component. How can we solve for these things? This is also where I strongly recommend the use of colored pencils, anything you can get your hands on, because it helps, especially if you're a very visual learner, it really helps to compartmentalize the portions of the overall problem. I'll do my vectors in colors and then do all my calculations in a box of that color. I'll still do it with pencil, but I'll take a highlighter and make a box that coordinates to the vector so I can visually track it. Okay, so what we know is that that angle of 25 in there, if we take the opposite, here's our delta y, here's our delta x. So the sine of theta is equal to delta y over our overall displacement for that segment. Therefore, sine theta times displacement is going to give us our delta y. Well, likewise, we can take cosine of theta, which is equal to delta x over our displacement. And we know that cosine theta times d will give us our delta x. Okay, sine of 25 times 157 meters. Oops, there. Sine of 25 times 157. We get 66.351067009 meters is our delta y. Cosine of 25 times 157 meters is our delta x. Cosine 25 times 157. Cosine, 142.29032, etc. equals delta x. I know I'm off the screen. Okay, so now we want to look at our overall triangle. This is only the first step. So if we look at our overall triangle, I typically pick a third color for that. So we've already done red for our resultant. I'm going to draw a red. So this is delta x total. This is delta y total. Now in this case, of course, there is no delta y on our first segment. Okay, so what we know, and this is our resultant. So we know that the square root of delta x total squared plus delta y total squared equals our resultant. Yes? Okay. So, we know that, let's get our delta x total equals delta x1 plus delta x2. This is delta x1. delta x2. So delta x total is 255 meters plus 142.290, etc. And we want to keep all those numbers. So the square root then of 142.2903226 plus 255 squared plus, now our delta y is all in that second segment. So here we have 397.290 meters squared plus, and delta y total equals delta y1 plus delta y2, that's 0 plus that number. So we get 66.35, etc. meters squared. Okay. Okay, so we get 402.7928307 meters is our resultant. Okay? We can have 3 sig figs, so resultant equals 403 meters. Now, are we done? One last thing we have to do. What do we have to do? We need to find a heading. 403 meters is meaningless if we don't have a direction to go with it because it's a vector. So this will be an angle above the horizon. And I'm going to, with your permission, I will get rid of some of this. Okay. Actually, I can get rid of it. I guess I'll get rid of all of it. Because I've got the numbers in my calculator. If you're using the TI multi-view, remember you can store a lot of numbers and pull them back down. Okay, so we would much rather use as few calculated numbers as possible to find that angle. So our best bet is our tangent function. Because this is a given, and these were our first set of calculations, so this is the fewest potential sources of our own error. If you use your resultant, of course, you've done these calculations and then used calculated numbers in another calculation, you can have a snowball effect if you've goofed something up along the way. So use what you can that has the fewest steps of calculation involved. So we know that the tangent of theta.
You could figure it out by just getting degrees, because that's a 90-degree angle, so you can make that.
Oh yeah, you could.
You could just
Well,
do that.
we did. Oh, you mean the angle?
Yeah, you could figure that out. By
Well, we
just
could, but we have to get one of those angles using a trig function.
No.
No, if you already have the top one.
25, the top one, since it's 90-degree angle.
Oh yeah, okay.
100
Well, wait. Yeah, okay.
65.
You could. You're right. You could in this case. Okay. However, still going to make you do it with the tangent because these are about to get more complicated. So, yes, you're absolutely right. You could, because I forgot. You've got the 25 here, so you can figure out that angle, and then you can figure. Well, no, because then you have to figure out the other half of that angle.
180 minus 25 to find that angle. So then that one up there, you found it by probably.
Okay, you could do that. That's more steps. It is actually more steps. But yes, you could. You're absolutely right. You could do this with a straight analytical geometry approach. You could. Do you remember what I said early on about physics? For every physics problem, there are 6 ways to get an answer. 3 of them are probably right. 1 of them's elegant. You're absolutely right. You could do analytical geometry on this, and you could get the right angle. I think it's easier to just do tangent opposite over adjacent, so that's going to be delta y total over delta x total, and it's one step. But you can do an analytical geometry approach if you want. So our delta y total was 62 or 66. So tan minus 1 of delta y total over delta x total should give us theta. Tan minus 1 of 66.35, etc. over our sum of our other two. $397.290, etc. will give us theta. So pull that down. Pull that down. Oops. Okay, second function, tangents. 66.35, etc. divided by our 397, etc. And we get a theta of 9.481406, etc. degrees. We can have 3 sigs, so 9.48 degrees is your theta. If you wanted to do the analytical geometry approach, let's examine that, because that's a good realization. You have to find this angle. That's easy. You find, well, no, it's not so easy. So you can find this angle, and you can find that angle. Well, okay, so then you know you have a right angle here, so you've got 180 minus 90, and then you get this angle. Whew. I think that's a lot of steps. It can be done. I know it can be done. I'd love it if one of you wants to do it. It exhausts me just looking at it. But yeah, it can be done.
That exhausts me.
Just doing a reverse tangent?
No, like the whole problem.
Oh, well, okay, that's all right. So we're gonna stop the video here for a moment.